So let's consider the second case of symmetry in Gauss's law, namely that of cylindrical symmetry. We'll start with the simplest possible example, namely we'll consider a long wire. In fact, we'll assume that it's infinite for a moment, and then we'll say that lambda is equal to dq by dl. I can't specify the total charge or total length because I've said that the wire is infinite. And we're going to say that lambda is uniform. With that, if we remember, at the midpoint of a short wire, the electric field pointed straight up, or at least when we were above the wire, pointed straight up. And this will now be true all along the cylinder. We expect the field to point radially outward. Moreover, we expect the electric field to be a fixed value when we are at a fixed radial distance r from our long wire. And for that reason, I'm going to propose that a surface which takes advantage of our symmetry would be a closed cylinder, centered on our wire, a distance r away. So let's think about how we would evaluate integral E dot dA in this case. So to begin with, there are three components of this surface. There are the two faces and the curved side. And remember, we need a closed surface for our evaluation of Gauss's law, so that's important. I'll begin by drawing the normal vectors to each of those three components. So for the curved section, we'll notice that our normal vector dA also points radially outward. Let's draw it below for clarity. On our two faces, dA points to the right and to the left, respectively. For that reason, on our two faces, E dot dA will equal 0 because E is embedded into the face, right? E is perpendicular to dA. So E dot dA equals 0 on faces. And so I'm going to rewrite our integral as the integral, drop the closed sign. We'll say integral over curve E dot dA. Moreover, now we can proceed with our old argument. E is parallel to dA, so drop the dot products. So we just have EdA. And then E is constant along our surface, so pull it out of the integral. Now to compute dA, I need to specify one more parameter. Namely, I need to specify what the length of our cylinder is. So we're just going to quickly label that lowercase l. And then we can say that E integral dA is equal to E times 2 pi RL. And again, this will be our result for every single case of cylindrical symmetry. You'll never need to redo this. Cylindrical symmetry, E times 2 pi RL. So now we need to compute Q enclosed. We can formally do this by saying dq is equal to lambda dl and integrating this. But of course, in this case, lambda is constant. So dq is simply lambda times L, the length of our Gaussian cylinder. And so with that, we can say E times 2 pi RL is equal to lambda L over epsilon naught. And this yields us the result that E is equal to lambda. L's cancel out, so lambda over 2 pi R epsilon naught. Now, importantly, something I want to point out is that L canceled out, and that is to be expected. Note that L is kind of an arbitrary choice of the length of our Gaussian cylinder, and therefore really should not show up in our final answer. So now let's consider one more problem along those same lines. Suppose that we have instead a solid cylinder with radius capital R. And instead of assuming it's uniformly charged, I'm actually going to jump straight to the case where we have a volume charge density. Suppose we have rho of R is equal to, let's say, alpha R once again, right? So we did a similar scenario with the sphere. Again, I'm not going to redo the left-hand side of Gauss's law. Integral E dot dA is going to equal 2 pi RL, where L is the length of now my Gaussian surface, which I'm choosing to embed at a radius less than the cylinder radius. And it has length lowercase l. Great. So integral E dot dA equals 2 pi RL. We simply need to figure out what Q enclosed is. Much in the same manner as we did with the sphere, we're going to rewrite this. Q enclosed will be equal. Remember that rho is dq by dv. This is still true. We are still dealing with a volume. And so Q enclosed will be equal to rho dv, or alpha r dv. Here's where we differ from the sphere. Remember, for the sphere, we said that dv is equal to 4 pi r squared dr. We did this by breaking up the sphere into thin spherical shells. For the cylinder, instead, we can break down the cylinder into thin cylindrical shells. And when we do that, consider a thin cylinder with length L, radius r, and thickness dr, right? So we're doing a cylindrical shell. Well, its dv, its infinitesimal volume, will be the surface of the cylinder, so 2 pi r L times thickness dr. So that's what we get for our dv. And so rewriting this, we have the integral alpha r times 2 pi rl dr, and our bounds of integration will be from 0 to r. So what does this give us? This gives us 2 pi alpha L, and we have integral r squared, which becomes r cubed over 3. So finally, we can put all of this together and say 2 pi RL. I just noticed that I had mistakenly dropped an E up there. We get 2 pi RLE is equal to 2 pi alpha L cubed, LR cubed over 3 epsilon naught. Some cleaning up to be done. One factor of R cancels, L cancels, and we're left with E is equal to alpha R squared over 3 epsilon naught. Now, importantly, this is, of course, for R, which is less than big R. What if R is greater than big R? In that case, again, we proceed the same way. The only change is that we take our integral and we switch the bounds of integration. Our charge density only extends until big R. So now our charge enclosed will be the integral from 0 to big R, alpha R, 2 pi R L dr. And I'll leave it to you to complete that case of the problem.